Hello and welcome back to part 2 of the PIC12F683 video series. To recap, we already did a cross-section of the device in the previous part, and now it's time to go depackage one and get a top-down view of the silicon itself. Okay, so now we have a cross-section of the device. We have a pretty good understanding of the materials and layer thicknesses that go into it. We also even have a good view of the metal stack up on top of the silicon, showing the various interconnect layers and their approximate thicknesses and spacing, which is going to become important when we start getting down to delayering later on in the project. The only problem right now is what we don't currently have is this top-down view, so we don't know the overall shape and position of the silicon die within the package, and we also don't know the mapping of pins on the die to pads on the package. And so for this reason, among others, we're going to want to prepare a sample that is exposed in the package with the bond wire still intact, so that we can trace out which pin on the package goes to which bond wire. And this will also provide us with the ability to do semi-invasive attacks, for example, UV light fuse resets, which I'm going to try later on in the video as well. So here's the overall outline of our package. There's a common misconception that the entire device is just covered in epoxy resin. This is not actually correct for a variety of reasons, including thermal expansion coefficient mismatch. The molding compound is actually a composite. It is a epoxy resin, typically filled with silica microspheres of various sizes, so it's closer to fiberglass, but with a particulate-based filler rather than with a fibrous filler. And so our goal in this case is going to be, we want to expose essentially everything in here. We want to expose everything in here while keeping enough of the package's structural integrity that we still have the lead frame. We can still solder it to a board. We can still pick it up and handle it. So ideally what we want to do is we want to create a cavity kind of like that, and kind of like that. So we've got some of the bond wire, at least the top surface of the silicon. We don't care if the paddle is exposed. It's probably actually better if the paddle is not, so that we still have this little bit of molding compound here providing structural support to the package, and the same thing here. So seen from the top, this is going to look kind of like this. So what we want to do is we want to clear out this part of the package and expose the silicon and the wire bonds while keeping the remainder of the package relatively undamaged, and ideally keep enough of it undamaged that we can still see, for example, the pin 1 laser marking right here, so that we can tell which pin is which. So zooming in a little bit closer on the edge of the sample, we've got the silicon die, we've got our bond pad, which we now know from the cross-section is aluminum, we've got our bond wire, which we now know is made of copper. A lot of older devices used gold, which was easier to work with because it was so chemically inert. It is also expensive, so for that reason, a lot of more modern devices have moved to copper, which is significantly less expensive. It is also harder as well as more reactive, which does pose some processing challenges during manufacture. It also poses challenges during deprocessing, as we're doing here. So we have, in this case, we're trying to create essentially a cavity in this whole area. So we've got these spheres of silicate filler all over everything. Oops. And then that's all in a matrix of a organic resin of some sort, again, typically epoxy based. And so we want to clear all of this out and not damage silicon, not damage aluminum, not damage the glass dielectric over the top. So let's just show the insulating layer there just to be a little bit more accurate here. So we don't want to damage the insulator, we don't want to damage the silicon, we don't want to damage the wire bonds, but we want all of the glass filler and we want all of the epoxy gone within a selective region, and we want to keep the package intact outside of this region here because we still want to have enough of the package left to handle. So this requires that we use a etching technique that is both chemically and physically selective. So we can achieve physical selectivity by a couple of methods. On larger devices like QFPs, you can just drop acid onto the center of the package. It's going to spread out a little bit, surface tension is going to hold it in place, and you get kind of a crater. And on a smaller package, often you need to use some sort of a masking technique in order to keep the acid exactly where you want, and that's what we're going to be doing on this device because, again, it is a fairly small QFN. We're looking at 4 millimeters across the entire device, and the die size is about 2 millimeters. And so we've only got, this is obviously not to scale, I've only got about 1 millimeter of margin on either side, and so we are going to need to use some masking to make sure that we have a lot of removal here and essentially no removal here, and we've only got a millimeter to work with. So our bond wires are made of copper with a palladium coating, and I believe there's a very thin gold flash over the surface as well. We can essentially ignore that. It's not thick enough to cause any significant corrosion protection. And so we want to be able to remove all of this material. This is typically done if you're just trying to recover a bare die for deprocessing, or if you're trying to depackage a gold bonded device. This is typically done with concentrated nitric acid, which is a strong oxidizer as well as an acid, and this will allow us to take all of the organic filler material and oxidize that into CO2 and water and other easily removable etch products, and then the silicate filler can just be washed away with a solid. Now, the problem is that although the glass passivation layer will protect the silicon itself is relatively inert to the acid, the aluminum actually is not too reactive with nitric either, but copper is extremely reactive to nitric acid, and it really wants to turn it to copper nitrate. So in order to prevent that from happening, we do have to tune the etch mixture a little bit. Nitric acid is actually an interesting chemical because of its oxidizing and acidic nature, and depending on the concentration and presence of other things such as water, one or the other may dominate in any given reaction. And so we want to maximize the oxidizing nature, and we don't want it to be behaving like an acid more than necessary. And so, somewhat counterintuitively, as the concentration of the acid goes up, proportionally speaking, and the water concentration goes down, it will actually be more inclined to passivate metals. So specifically the copper, as the acid concentration goes up, you will form a copper, I believe, oxide and nitrate mix layer on the surface, which, if you don't have any water present at all, will not dissolve into the acid and will therefore provide a passivation that protects against further corrosion. Unfortunately, I don't have access to fuming nitric acid. It's both very expensive and also quite unstable, and in a personal lab, I don't really want to keep it around. On the other hand, 70% is significantly more stable. It's much easier to get hold of from general chemical suppliers. It's not like a specialty exotic material. Unfortunately, 70% nitric will eat copper immediately. So the best results that I've had are actually by mixing concentrated sulfuric with the nitric, and so the sulfuric acid behaves as a dehydrating agent. Now, the sulfuric will oxidize the organics if you get it much, much hotter, like 200-300 C, but we're not going to be working anywhere near that hot. When the sulfuric is present at lower temperatures, it will dilute the nitric, but do so in an anhydrous environment that still keeps the pH very low, and the sulfuric will try to grab onto the remaining water in the nitric and give us essentially a reaction environment that is free of available water. So we get the nitric reacting with the organics. The silicates essentially just sit there and are flushed away during the cleaning stage, and the sulfuric is going to hold on to both the water generated by the breakdown of the epoxy as well as the water present in the 70% nitric. And so ideally what we get is this film of passivation material on the surface of the metal. We've just got a few nanometers, even just maybe a couple of monolayers of this passivation on the surface of the wire that protects it from further corrosion, and then all of the other materials in the package are removed. So for that, we're going to go mount the device up on top of this heatsink. This is a random aluminum M2 heatsink that I had lying around. It's relatively chemical resistant, relatively thermally conductive. And we're just going to tack it down first with a little blob of UV glue over here just so it doesn't move. Blob there, a little blob there. And this is a removable wire tack adhesive that we're using here, so it should come off without any residue. Let's give it 2 hits just to make sure it's secured all the way. And look from the side. Okay, yeah, looks pretty well secured. So now the next step is going to be to cover the sides and the pins with our removable masking material so that we don't have any acid damage to parts of the package that we're trying to keep. I do know that the size of the die is about 2 millimeters on a side roughly, and the package is around 4 square, so we want about a 1 millimeter boundary around there. But before we do that, we're going to have to start building up the mask on the side of the package. Just going to start building up some of this masking material on the side, and then we're going to continue on here. Make sure you get good coverage. This is the first time that I've tried using this particular heatsink. I've used a flat surface in the past and I've had some issues with it as far as delamination and so on. My hope is that any acid overspray and so on with the heatsink will just fall down into the channels and fall away from the device. And so we're not going to have to worry too much about corrosion on the underside. I'll probably see if I can get a little bit of the mask on the underside just to be safe, but I don't think it's going to be necessary. And I just realized that I'm outside the field of view here. So we're going to get that on there. And then So now we're back at the wet bench preparing acid for the partial decap. This is not going to be a full tutorial on sample preparation or on lab safety, just a few things I'm going to point out. In this case, we're using concentrated sulfuric and 70% nitric. This is a suboptimal mixture, but it is a little bit safer to store than some things like fuming nitric, which are also a lot more expensive. And for both the volume and the nature of my lab, this makes a little bit more sense. And now we've got our acid mixed and we've got the sample preheating. We have the cleaning solvent, which is just acetone prepared in a syringe with a blunt needle for rinsing. This allows a much higher pressure stream than you would get by just swishing the sample around, and also goes through solvent a little bit slower than in a wash bottle, and actually allows higher pressure in some cases. So now we've got the acid on the sample and we're letting it sit there and react. One of the important things when you're trying to preserve copper bond wires is making sure that as much of the process as possible is anhydrous. Any water will degrade the passivation layer, so in this case we're using the sulfuric as a dehydrating agent to sequester any of the water in the 70% nitric, as well as anything produced by the reaction, and then using relatively dry acetone for the rinsing process as well. We do also want to use a large quantity of solvent during the rinse cycle. The reaction with any residual acid is somewhat exothermic, and so to avoid any unwanted self-heating or possibly even ignition, we want to make sure that we flood the sample with solvent and bring the temperature down quickly rather than letting it sit there and react slowly with just a few drops of solvent. Not that it would be the end of the world if there was a small amount of exotherm going on there, but it would certainly damage the sample. And now we have another drop of acid on there and reacting, and this is actually a little bit more vigorous than I like to see. It reacted a little quickly, so I think I'm going to turn the hot plate down in a couple of seconds. Yep. There is usually a little bit of experimentation involved anytime you're playing with a new sample mounting fixture, since you aren't usually controlling the temperature of the sample directly. It's too small to get any kind of a thermocouple or anything on. Typically, you're just controlling the hot plate temperature and then relying on that as a proxy for sample temperature. And so figuring out what to set the hot plate at to get your sample at the desired temperature can be a little bit of art. I usually find around 140-ish with this particular hot plate, and this particular sample holder works decently, but... And now rinsing again. And inspecting, it looks like we're getting pretty close to, I think there might be some bond wire starting to show at this point, so I'm inspecting to see if we're actually there yet or if we want to run another couple of cycles. The original audio for this was completely wrecked by the noise of the fume hood blower, so the voiceover was the only option here. And cleaning again. One of the problems I had had with previous setups was the sample delaminating from the holder, and I was using flat surfaces for that, and so the fins on the heatsink are helping with maintaining adhesion of the sample to the holder by having a little bit more contact area. The trade-off is that, as seen here, there is a little bit of acid spray getting onto the underside. I don't remember if any of the video clips actually showed it, but there was a little bit of corrosion on the underside of the sample, and so that is something I'm going to be refining a little bit further. And then grabbing a little bit more solvent for rinsing. It actually took a little bit too much. It's hard to get my finger back on the syringe when the plunger is all the way back in these heavy gloves. You can see it's squirting out a little bit, which is not great, both from a making a mess perspective, and obviously the more solvent you have sitting around the hood next to strong oxidizers, it does somewhat increase the fire risk. And so at this point, I unmounted the sample from the holder and decided to both take a look at how the process was going. We can see we've got bond wires exposed on 3 corners, but the other reason is that although the mask had not degraded to the point that I was worried about it undercutting, there is one corner at the top right here where it looks like the mask was actually a little bit too tight and is covering a corner of the die, and so I decided I was going to take it off and make the mask a little bit looser. If you don't have an x-ray of the package, figuring out exactly how big of an aperture to leave and where to place it can be a little bit of an art form. So in this case, I apparently cut the corner just a little bit too close. So I've reapplied the mask off camera, leaving a bigger aperture above the sample in order to hopefully etch out that corner a little bit more. This was a little tricky because I was able to use a aqueous clean on the heatsink to get all of the sulfuric acid residue off of it, but there was still some in the sample. The nitric cleans off nicely with acetone. The sulfuric is less soluble and tends to kind of leave residue on things that requires a lot of water to get off, and that's not compatible with an in-process clean with this process, since it'll damage the passivation layer on the bond wires, which are now exposed. So now I'm just doing one last inspection and checking to see. It looks like I think I'm going to do one more drop of acid and then call it done and ready to take off. And then after removing it from the heat for the final etch cycle, then off camera I did a full aqueous clean, which is okay since we're not going to be doing more acid etching at this stage, and then sonicated a little bit to get the last of the debris off, which is a little tricky since you don't want to damage the bond wires, but a few seconds of sonication will make a big improvement in surface quality. So here's the sample after cleaning. we can see a nice square cavity around the die with all the bond wires exposed except the one in the bottom right corner, but we don't care about that area too much. The active circuitry is all fully exposed, and no damage outside the intended etch cavity. And just to show how far things have come, this is another decap of the same chip that I did early on when I was starting out. This is in the 8-pin dip package. You can see it's got a little bit of gold residue on it from SEM imaging years ago. But the important bit I want to call out here is the right side of the package is completely obliterated by acid spilling out over the edge and bubbling up, and also the diameter of the cavity, which is more rounded than rectangular, is just enormous, and there's so much destruction around the die. If this had been a small QFN or something, it would be gone. But with my more refined technique, the package is much more intact, and we can actually still read some of the laser markings to tell which pin is which gives us this pinout map. So after a couple of seconds of sonication in Micro 90 detergent solution to get the last of the packaging residue off, here we are under the metallurgical microscope. At the moment, I've got some low angle illumination turned on as well, so we can see the wire bonds a little bit better. And we can see they are intact. There's actually still a little bit of palladium on this one. Let's go zoom in more, switching to the 20x objective here. We can see a little bit of the palladium coating is still intact on this wire, and then as we get a little bit further down, there are some areas sticking more out of the molding compound that are exposed with just very, very light surface corrosion, but almost nothing, or sorry, surface pitting. Any corrosion products have been washed off by the clean. One little crystal on the side of that one. But wires overall in very good shape. Going back to the 5x objective, we can just about fit the entire sample in one field of view. We lose a little bit of the pad ring, but that's not a huge deal. So we've got our power pins, VDD here and VSS there. As we deprocess, we're probably going to see one of these two rings, this one and this one. My guess is that the outer ring is ground and the inner is VDD, but we'll know more once we've deprocessed a bit and see what these pads are actually connected to. Also, while we're still looking at the 5x overview, just to get you oriented as far as the various images we're looking at, this is the cross-section that we took in the first part of the video. And so we are looking in now from the right side of the image. And so this bond wire right here, which is the VSS bond here, that is this wire here. Then we've got GP0 here and here, GP1 here, and GP2 here and here. And so we're looking in essentially this whole side with the sectioning plane tilted slightly to the right of vertical. So we're dead center in these bonds, and then, dead center in these bonds, and then just slightly inboard. So we're at maybe a degree or two counterclockwise of perfectly vertical in the cross-section plane. And then as we switch to a higher magnification view, this is with the 20x objective. We're going to go down to the bottom right corner and take a closer look at the GP1 bond pad. And seen here in cross-section, this is this bond on the other test sample. And so we can see that there's this little wire here is probably this one here that we're looking end on. And then we've got 1, 2, 3 metal layers with some vias visible between them on the perimeter of the bond pad. And then on either side here, we can see a little bit of squeeze out. That's pretty typical. If you etch off a ball bond, you'll see a noticeable crater in the pad where the bond had been. And now looking at, this is the top left corner of the cross-section, and the actual area in question is blocked by some of this molding compound that wasn't fully etched in our partial decap sample. But if we go down to the bottom left corner, the layout of the pad ring is pretty symmetric. And so we can see that this section here is this outer seal ring, and metal 1 is a little bit fatter and sticking out more. So we can see metal 1 over here is overhanging, and then metal 2 and 3 are almost the same size. We can't really see the difference easily in the top-down view at this scale, but that's metal 2 and 3 right here. And then
This stack here, this is all 3 metal layers on this, which I'm guessing, again, is probably ground, but we don't have enough information at this stage of the process to know for sure. And then moving to the right a little bit in the cross-section, so now we're looking at this area around here, just a little bit up closer to the first ball bond, so that's the GP2 ball bond. Now we're looking at this, and again, the actual image is coming from the right side, but that area is partially blocked, so we're looking at the essentially symmetric area on the left. So there's a little bit of dummy fill just below that right-hand bond pad, and so this is probably that area of dummy fill, except this area right here that, again, is mostly covered. And then down in the bottom left corner now, we've got some interesting die ID markings. So Microchip typically labels all of their masks with a 5-character code. This looks like DE024. You'll note that there are no small holes in the zeros or the D. This is presumably for fabrication reasons. Maybe on the big upper metal layers they can't have small holes, or there might be some technicalities of the mask manufacturing process where they want to avoid having floating features or anything like that getting etched off. But anyway, that's usually 2 small characters and then 3 big ones. As far as I know, there's no inherent meaning. Going from even 2 devices in the same family, the mask codes seem to have nothing in common. So I don't know how they're generated, but anyway, that's very typical of a Microchip part. Then we've got the actual Microchip logo and copyright notice here. Interestingly, no copyright year on the die, just a copyright mark. This part is quite old. It's, again, a 350 nanometer node. And I have been personally using it since I was an undergraduate back in like 2009 or something is when I first started playing with it, maybe even earlier. And so it is no spring chicken, but being such an old node does make it really easy to fully reverse engineer everything we care about optically and not need SEM or anything, which is nice for a home project. And then over here, we can see we've got mask IDs for 3 of the layers. So this one is pretty clearly poly. And then this is metal 3. And this is metal 1 or 2. It's a little hard to tell which is which. And then I believe if we go up somewhere in this area, yeah, we've got the revision ID for the other of the lower metal layers. I'm not sure why they stuck it up there. I'm guessing they just ran out of space in the original corner. One interesting thing about this particular process is that the vias actually have slightly larger annular rings on the ends of the tracks. On most modern nodes, the vias are the same diameter of the track or even slightly smaller, and so you can't actually see a via from the top in an optical image because it's the same width as a normal track. You can often see some higher backscatter yield in SEM, especially on aluminum process where you've got a low Z aluminum conductor and then a high Z tungsten via plug under it. But in optical, obviously, you don't get backscatter contrast, so you don't have any of that information. But it is interesting that this looks a lot more like an older process where typically on the like non-planarized 800 nanometer or 1 micron and up scale nodes, it was very common to see big annular rings on the ends of traces, and you could even often see a little bit of a divot in the center where the actual via was. And so it doesn't look like there's an obvious depression where the vias are. There's maybe a tiny little dot, but not too significant. But the wider area does give us a good indication that, for example, right here, there's probably vias. And these traces here, not seeing any vias in them at all, are likely dummy fill. And then going down to the mask ID markings with the 100x objective, we can get a little better sense of the height here, shifting the focal plane from, in this case, this is poly, and then going up to metal 1 or 2, and then focus now on metal 3. You can get a better sense of depth with the narrower depth of field. And now we're back to the wet bench again, this time preparing a bunch of bare die so that we can deprocess them to look at lower layers. We are doing 5 PIC12F683s as well as 4 unrelated samples that I just threw in as long as I had free space in the beakers. I put a few of the samples off to the side because I can't fit them all on the hot plate at once, and also, if you'll notice, the acid was turning green already, and sometimes if you've got a big thermal pad, the sample will start to react a little too aggressively, and to keep from boiling over, I'll let it sit at room temperature and kind of eat through a bit of the copper before I start heating. Also, I'm using a ductless fume hood, so you'll notice most of the beakers have watch glasses over them just to retard evaporation. This both reduces acid loss in the small beakers so that you don't have too much boil off. You get kind of a reflux going on, and it also leads to the filters wearing out less quickly since you're not dumping quite so much nitrogen dioxide into them. Instead, you end up boiling off water, and some of the nitrogen dioxide will dissolve back into it and drip back in, and you end up with a continuous reflux, and not a whole lot of acid is lost. So I'm periodically removing some of the big samples to check on them, swishing them around in some acetone to rinse them. You do want to shake off as much acid as possible when doing this so that you don't have too much of a reaction. We don't care about keeping bond wires intact, though, in this case, because we are trying to get bare dyes. And you'll see as samples finish up, I'll pour the waste acid into a inspection beaker first so that I can decant it back into the original beaker if it needs more time. And then when I've determined that the sample is done, I'll pour the waste back into the waste beaker that you'll see at the very top of the frame in the inset and let it react with some sodium carbonate that I have sitting there. The goal here is twofold. First of all, neutralize any residual acid in the waste. I tend to keep my waste around for a while because I don't generate a whole lot of it, and it's not worth making the trip to a disposal site just to drop off a few milliliters of it. And so I want it to be in a essentially shelf-stable form that I can keep around for a couple of months before it's time to go make the trip down to get rid of it in a safe way. And the second related reason is you'll notice that the waste is green. That's because there's a lot of dissolved copper salts in it, mostly copper nitrate in this case since we're decapping with nitric acid. And soluble copper salts have fairly high bioavailability and are quite toxic to wildlife. And I don't want to be cleaning off my glassware and having copper salts getting down the drain and so on. And so by neutralizing it first, most of the copper precipitates out as copper carbonate, which I can then filter off. And then I'll give all the glassware a quick wipe with a paper towel, hold on to those as essentially heavy metal waste, and then whatever's left over can then be cleaned off with tap water, and I don't have to worry about polluting anything. And so now I'm just taking the last couple of samples off and cleaning them. And now everything is done, and I'm deconning the hood. You'll see the only thing left is the waste beaker, and now I'm just setting it up for filtration to filter off as much of the copper carbonate as I can. A good chunk of it comes out as particulates. Some will stay in solution because it either didn't completely react or the pH was not quite perfect to precipitate it. So that gets put in a separate waste jar and just held onto until I can take it to a disposal site.
Okay, so now we have a bunch of bare dyes and we want to go see what's under the surface. We already know from the cross-section that we've got 3 metal layers, and I'm just going to draw a illustration of what we actually expect to see. So we've got our silicon substrate down here. We're going to have our isolation trenches, and then the active transistors are going to be up on kind of islands with isolation between them. Then we'll have our dielectric that's too thin to see. We've got our polysilicon gates going up above them. Contacts going from that up to, contacts should be that tall. Contacts going up to our metal 1. And then above metal 1, we're going to have metal 2, and then metal 3. And there's also going to be a little bit of roughness on the top surface, so the top passivation is actually not going to be quite flat. It's actually going to be kind of more like that, where it flows over the surface of the top metal layers. The lower layers are planarized. The surface of the wafer is polished flat in between. This is done both for lithography reasons, so that the depth of field of the imaging system isn't going to be affected by height variations in the surface. And on more modern devices using copper metallization, this is also actually an actual fabrication step, because the copper is not possible to plasma etch. But in this case, we know from the cross-section as well as just from the general age of the device that this is an aluminum device. And so zooming in a little bit more at the metal layers, what we're actually going to see in cross-section, if we look at each layer, they're actually going to look a little bit more like this. And then we're going to have top and bottom cap layers that I'll get to momentarily. I am somewhat exaggerating the slopes and the layer thicknesses just for clarity. And so we're going to have a bottom layer, typically titanium nitride, that is used to stick the aluminum to the surface a little bit more thoroughly so it doesn't float off during etching and such. And then we have the actual aluminum conductor that carries the bulk of the current. And then up top we have another cap layer. This is typically titanium or titanium nitride or some combination thereof. And then as we go down from this layer to the next layer down, we're going to have the vias are typically on devices of this generation, they're going to be tungsten. And then going down from there, we've got the cap layer on the next metal layer down, and then our aluminum conductor, and then our adhesion layer below that. And so we have a total of 3 conductor layers and then the polysilicon below there. So our goal is starting from this top surface, which as I mentioned is a little bit rough. We want to go down 1 layer at a time as precisely as possible. And there's a bunch of different techniques out there for doing this depending on the era of the device, what fancy toys you have available, what the individual layers are made from. The good news is that the choice of which technique to use is pretty much made for us, because I don't have a fancy polisher, I don't have any plasma etching tools, I don't have the space for them, they're also expensive, and so pretty much we're down to wet etching as the only option. And so now the question is, okay, what etch chemistry and what exact process do we want to use? So the dielectric is a silicate material. It's not pure SiO2. It's typically some sort of a CVD oxide. There could be some spin-on glass in there, but it's usually going to be CVD of silane or TiOS based. And so it's going to be a lower density, not completely solid silicate. There are going to be small voids, and it's not a monocrystalline fused quartz or anything like that. But for chemistry purposes, we can mostly treat it as just glass. This especially, we're not dealing with any of the super modern stuff that are doing low-K organosilicates or any of that. This is all old school, again, 350 nanometer nodes. So the only real option for wet etching that is hydrofluoric acid, which I do have available at a comfortably low concentration of 2%, which is still scary, but slightly less scary than the 49% that is used in more serious labs. I don't want that in my house. And so as we start wet etching in from the top, what we're going to see is we're going to hit this top layer, which again is probably titanium nitride or something along those lines, and that is relatively resistant to attack by the HF. And so as we continue etching in, we're going to hit, there's usually a thin spot in the top. So the top layer is actually, I forgot to mention, the top layer is typically silicon nitride in the cap, and then under there, below the silicon nitride, is oxide-based dielectrics. But typically the very top is nitride because that's a little bit harder. It provides a better protection to the device during packaging and handling and so on. Good news is that HF will eat nitride as well as oxide. So again, there's usually going to be a thin area on the edge of here, right where there's the humps over these metal layers. So we will start to get some HF coming in thinning out the dielectric, and eventually it's going to start hitting the side of the aluminum. And HF will also eat the aluminum. We'll get aluminum fluoride and probably some other reaction products, because the aluminum is not pure aluminum. It's usually got a little bit of silicon or some other materials alloyed in with it. But for our purposes, for the most part, what we're going to be getting is aluminum fluoride, which should dissolve into the etchant. And now we're going to have this unsupported top layer, which will just float off because there's nothing holding it in place. And now what we get is, if we erase this, what we're going to get is we've got our dielectric layer. We've now eaten away some of the aluminum. So now we've got this hole where the aluminum was. And we've got our tinitride at the bottom. And so that's going to provide a barrier against further etching in the downward direction, but the HF etch is isotropic, and so it is going to slowly start eating outwards towards the side. It's going to eat away this undercut, and at the same time we're also etching it from the top. So eventually we are going to remove most of the glass. We're going to get down to this area. We are going to start undercutting the tinitride, and at that point it will eventually float away and be removed. And so kind of part of the art here is there are various techniques you can use with sonication and just swabbing the surface of the die and so on to remove loosely attached materials that are either completely floated off or beginning to delaminate. And so figuring out exactly when to use some of these more aggressive techniques to remove the tinitride, which will enable etching in the direct downward direction, as opposed to allowing it to be undercut, because what we don't want to do is we don't want to create a pedestal where we've etched down a bunch more and we have this tinitride layer here, and now we've got something like this where we have our glass layer below it, and the HF is slowly eating in from the edges and is not doing a whole lot to the top, and we end up having this hump of dielectric, which is going to cause shadowing of lower layers. And again, some of these effects are impossible to eliminate. This is the reason why wet etching is not used in serious deprocessing, especially on more modern nodes.
Over the course of about 2 weeks, I did a total of 27 etch cycles. The device was imaged 66 times at 20x and or 100x magnification, sometimes after cleaning steps as well as etch steps. The total data set acquired from all of this was 203.5 gigabytes, just under 370,000 photos. And in the end, we have the entire device imaged at full transistor level resolution on every layer. We can see every wire, every via, every conductor, and also some interesting tidbits like how the analog areas have higher glass density and lower metal density, so they etch slower.
And we're coming up on the 45-minute mark, so I'm not going to keep you any longer. This is the end of part 2. Stay tuned for part 3 coming soon, in which we're going to start looking in more detail at the device floor plan, get a better sense of where the major functional blocks are, and then get ready to dig deeper into the circuitry of individual devices.